Yeah, so that's a constant tussle. Many applications, smart healthcare, for example, I want to distinguish disease from non-disease, disease from healthy. I need to collect a lot of data, which is not easy to collect. So an alternative, and that is gaining steam also. There are many startups being formed just on the basis of synthetic data. So if you can draw synthetic data from the same probability distribution as your real training data set, and now pre-train your neural network so that it gets into a good place, so that next when you train it with real data, it gives you very high accuracy. So that's something that we've looked at. We've developed a tool called Tutor, which does that, and others are also looking at the applications of synthetic data so that the need for big data becomes less and less as we go forward.
But when I read the tutor paper, I noted that you were sort of mimicking the brain, right? Can you tell us a bit more about that?
Yeah, so there are many ways of mimicking the brain. In fact, if you go back to the 1943 paper, McCulloch and Pitts, they defined the artificial neuron model after our brain. We have about 100 billion neurons. We have about 100 trillion connections among those neurons. And so they defined, inspired by the brain, the concept of an artificial neuron, and others took it forward, connected these neurons together, and the concept of an artificial neural network was born. But for the longest time, that's where the inspiration stopped. And so biological neural networks and artificial neural networks diverged a little bit. But now there is feedback that we're getting from neuroscience, and there are neuromorphic architectures that try to mimic the brain. Then in our own work, not just in Tutor, but there is a tool called NEST, which is for image data. There is a tool called SCAN, which is for sensor data. The way we mimic the brain is the way our brain develops. So I don't know if you're aware that you were the smartest when you were a toddler. And the definition of smartest here is maximum number of connections in the brain. So after that, it is all downhill for us adults. So from a baby brain, you grow to a toddler brain and you gain accuracy. You train the neural network by adding neurons and connections to increase its accuracy. But then you're interested really in one particular application. Maybe it's diagnosis, maybe it's cybersecurity. And then you try to reduce the number of connections through pruning, and you get an adult brain equivalent, which is very good for that particular job. Unlike the toddler brain, which is a general purpose learning machine. Your toddler is extremely smart, and you were extremely smart when you were a toddler. So we try to mimic this approach when we combine this synthetic data plus the real data, and then using these two, we want to train and synthesize neural networks that are very compact, very memory efficient, very energy efficient, latency efficient, very compatible with the edge. So that's some of the inspirations we are taking from the human brain in our own work. But there's a lot more going on in terms of inspiration from neuroscience coming back to computer science.